Welcome. Today we are discussing Module 6.1, the Retrieval Process and KNN Algorithms, Theory. Here is a quick look at where we are in our curriculum. Hello everyone, and welcome to our series on Enterprise LLM Production Patterns. Today, we're diving deep into the mathematical core of modern AI, the dense retrieval process and k-nearest neighbors. When building production RAG systems, the bottleneck is rarely the LLM generation itself, it is the quality of the retrieved context. Traditional keyword engines fail when users ask questions using synonyms or complex syntax. By projecting text chunks into high-dimensional vector spaces, we can capture pure semantics. In this module, I will guide you through the raw mechanics of similarity search, showing you how computers turn semantic meaning into physical coordinates. Let's look at the ingestion and query flow to understand how raw text becomes searchable vectors. To understand retrieval, we must understand space. There are three core metrics we use to measure how close two vectors are. First, Euclidean distance, or L2 norm, calculates the straight-line distance between 2 points in space. It is highly sensitive to vector magnitude. Second, cosine similarity measures only the angle between vectors, completely ignoring magnitude, which is perfect when document lengths vary. Third, dot product measures both angle and magnitude. If your embeddings are perfectly normalized to unit length, dot product is mathematically equivalent to cosine similarity but operates much faster because it skips the expensive square root divisions. Knowing when to use which is critical for optimization. Now let's examine the classical k-nearest neighbors, or KNN, algorithm. When a user sends a query, our database translates it into an embedding. KNN takes this query vector and performs an exhaustive calculation against every single vector in our database. If you have 10,000 documents, it does 10,000 comparisons. If you have 10 million, it does 10 million comparisons. While this exact search guarantees absolute accuracy, it scales poorly. For large enterprise systems, this exhaustive search is too slow for real-time applications, which is why we must understand the trade-offs of exact search before looking at optimization indices. Let's trace how a complete query lifecycle flows through an index to understand this visually. To truly master this, we shouldn't treat vector search as a black box. Let's look at how we build this from scratch using NumPy. I have written a production-grade script that demonstrates exactly how cosine similarity is computed under the hood. In this script, we initialize a mock database of high-dimensional vectors, generate a query vector, and perform normalized matrix multiplication to instantly get our similarity rankings. Please make sure to check the link in the description to download the architecture diagram and this Python script so you can run it locally and experiment with different vector dimensions. Let's review the output on our terminal when we execute this custom retrieval. As you can see, the index scan successfully identifies the top 3 most semantically relevant vectors along with their precise cosine similarity scores. In our console, we see document index 429 scored a similarity of 0.14, while others dropped off rapidly. In a production pipeline, you would use these indices to instantly fetch the corresponding raw text chunks from your primary relational database and feed them into your LLM prompt. This bridges raw linear algebra with the actual context ingestion. Now that you understand the mathematical foundation of vector spaces, similarity metrics, and exact KNN searches, you are ready to see how the scale problem is solved in the real world. In real-world enterprise applications, writing raw NumPy multiplication loops is not viable. We need robust systems that can handle database connections, metadata filtering, and real-time document streaming without breaking a sweat. In our upcoming lecture, Module 6.2, Implementing a basic retriever chain, practical. I will take you hands-on with LangChain to build a production-grade end-to-end retriever pipeline. We will implement vector stores, build an active chain, and run real semantic queries. Thank you for joining me today, and I will see you in the next lecture.